Alright, so for the next topic, well, this one should be a 2, not a 1. I don't know where it's a 1. So it's finding the area under the polar curve. Well, for polar curves, this is the way we are going to define the partitions. It's going to be a little bit different, but ultimately the same in the sense of how we find the infinite sum in terms of a Riemann sum. All right. Well, from basic geometry, or also in trigonometry, you learn how to find the area of a circular sector, and that's to multiply the radius squared times the angle and divide by a half. All right. Now, suppose that we have a function or a curve defined in the polar system. All right. Some r equals f of theta. You know, like a cardioid, like a limosone, or a flower with many leaves, right? Well, in this case, we are not going to find the area under the curve by rectangles, because that's not how we are defining the function. This is not a function f of x equals to y in which delta x is the width of the rectangle and the height is f of x or y in this case. No, it's the way we're defining these functions is different. We're defining the functions in terms of radius and angle. So for different radii, we're gonna have this ray right here, and as a really small increment, you know, to go from theta sub I minus 1 and theta sub I, we can rewrite this in a more compact way as delta theta. You know, that's the differential. In a very similar way that in the area under the curve, we had that delta x like the x2 minus x1, you know? So, or x sub I minus x sub I minus 1, depending on the symbols that we used. And of course, in the very same way is the more mini circular sectors that we define or that we partition this polar curve will give us a better approximation, a more refined area. How many partitions again would be good? How many? Maybe 3 partitions, 3 sectors would be a good approximation of the area. Maybe 10. Infinitely many. All right. So that's what the Riemann sum does. Add infinitely many of these partitions to get the actual, well, in this case, area. So, for example, let me derive this real quick. I think this. Yes. So for example, if we have the area of this symbol right here, which looks like a pizza slice, well, that's the area of the circular sector. All right. So that's 1/2 r squared, but in this case, I'm going to call this r sub I, because that's the sample, the partition I'm taking, and theta sub I. All right. So in this case, well, actually, let me change this to delta theta sub I. All right, because we need to find that length, you know, that distance from one angle to another angle in just the same way we got the delta x in by finding the area under the curve. Well, the area will be approximately the sum from I equals to 1 to n 1/2 r sub I squared delta theta. All right, so that's again the idea of the approximation first. All right. However, this is only the approximation. If you want the actual area, so if you want to change this approximation sign into an equal sign, what you want to do is add again but in this case, let me have the 1/2 outside. You might want to find the limit as n approaches infinity. And that's again the definition of the integral based on a Riemann sum, sub I. And in terms of integrals, this will be 1/2 the integral from alpha to beta of r squared d theta. Recall that when we go from finite calculation to infinitesimal calculation, the delta becomes a d, as a lowercase d. That is a differential rather. And of course, I mean, there's other versions of this formula as stated in the definition below. So instead of defining r squared, that's because r is f of theta depending on what notation we're given. So either way is fine. All right, the two are okay. All right, so let's do one example. Find the area of one petal of the rose curve given by r equals to 3 sine 2 theta. All right. So how about we graph it first? Clear. And let's see. So 3 sine 2 theta. Okay, before hitting the graph button, let's see if you remember what would you expect to see before clicking graph. Well, it's a rose, right? We already got that from instructions. And well, the question is how many leaves will it have?
It should have...
Tiffany? 4? Recall that when the number that multiplies the angle is even, we will expect to see twice as many leaves as the number. If the coefficient is odd, well, then we will just see 3 or 5 or 7. I mean, this is not something I would expect you to memorize, nor it's something that I would ask you on the final exam. It's just something, I mean, about pattern recognition that it's pretty cool to see anyway. So let's see. Well, this is not what I was expecting. 0. Yes, that's what I was expecting to see. All right? 4 leaves in this case. Well, let's draw the graph real quick. Yes, we're going to need it. All right, so we want only one petal. And I mean, you can choose your favorite petal to find. However, typically we go with the easiest one, the one that it's going to give us the smallest values of the angles, right? So what we're going to do in this case then is find the area under the first petal. So let me highlight with a different color. So we want this. That means we need to see how is the graph going to go from which angle to what angle. And well, so we need to set this equation equal to 0 in the same way that you want to find the points of intersection or the roots of an equation. You know, you set it equal to 0, and well, so in this case, you will get those solutions. And another way to visualize this is because, do you see where the loop starts here? It starts at the origin when r and theta are equal to 0. So if we start drawing the graph, this will generate the area in yellow. And then once we're done with the first loop, we're going to go back to 0. So that's why we're setting this equation equal to 0. All right? So let's see. So r equals 3 sine 2 theta. Well, we need to set this equal to 0. All right? And well, sine 2 theta equals to 0 over 3. That's 0. And well, for this trigonometric equation, be careful. So we are looking for the angles for which sine of 2 theta equals to 0. So for which angles is sine equal to 0 again? Number 1, 0. Is there another angle for which sine equals to 0? Well, another pi, and then 2 pi, and then 3 pi, 4 pi, etc. Okay, the reason why I'm listing a few more angles this time is because we have a composition function for the trigonometric function, and that may affect the number of solutions that we get within one cycle to pi. And we need to be very, very careful with this kind of equation. So need to keep in mind that this is 2 theta. So in this case, let's divide both sides by 2. So the real points of intersection between, or yes, intersection or the zeros of the function will depend on the point of view. So that's going to be theta equals 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. And the pattern continues in this case. All right. Well, and I think we can now visualize this, this graph with the points of intersection. I think this is going to go from 0, go around the first loop, and then end up here at the angle pi over 2. The second loop right here is going to go from pi over 2, go around the loop, and what's the angle here? Pi. Isn't it the next angle? What about the third loop? Starts at pi, goes around the loop, and what's the angle right here? All right, does that check? And of course, I mean, you can find the area of your favorite loop, but I mean, let's keep it simple. How about from 0 to pi over 2? All right. So area equals the integral from alpha to beta of r squared d theta. Don't forget the 1/2. All right. And well, r theta is going to be our function squared. 1/2 from 0 to pi over 2. And that's, be careful, r, or rather, so not r, it's 3 sine 2 theta. Quantity squared d theta. And okay, let's see. I'm gonna make a mistake here, see if you can catch it. All right. The 3. We also need to square the 3, right? We square both the coefficient and well, we can write it the following way. Let me go to the next page. So that's a negative 9, or no, not negative. It's 9/2. The integral from 0 to pi over 2 of sine squared 2 theta. Okay. How do we go about that integral? Final exam review. I think this is going to help a lot for final exam review. Would a U substitution work in here? No, definitely not. Because, well, we have a composite function, a sine squared. We wish we had the derivative of sine, which is cosine, outside, but we don't have it. Any other ideas? Yeah. Identity. Which identity, Jennifer?
1 minus cosine.
Cosine. Okay, 1 minus cosine 2x over 2. That's sine squared x. All right, that's in general with x. So what happens? We reduce the power, but we duplicate the angle. But be careful with the integral that we have here, because our angle, it's already at 2 theta. That's going to become then 4 theta. Also, another version that I highlight, that I highly recommend use instead, 1/2 1 minus cosine 2x. Right, this way it's easy to see the fractions and just take them outside instead of trying to do weird distributions of fractions, which is a very common mistake I've seen before. So that's 1/2 1 minus cosine 4 theta d theta. And well, so we can take that 1/2 outside and multiply with the 9/2. That's 9/4 integral from 0 to pi over 2 of 1 minus cosine 4 theta d theta. And well, I know it's possible to do this integral in our head without distributing, but I strongly recommend that you distribute this into two integrals. Number one, 9/2, or rather 9/4, integral from 0 to pi over 2 of d theta minus 9/4 integral from 0 to pi over 2 of cosine 4 theta d theta. And then, well, we can integrate the first term. That's the integral of d theta. That's just going to be theta times 9/4 minus 9/4 that multiplies the integral of cosine. But what's the integral of cosine? Negative sign? Sine, right? Positive sign. I'm going to leave a space for something. Sine 4 theta. What's that space for? 1/4, right? These are typically called the shortcut rules for the simplest compositions of sines, cosines, exponential, when you have simply a number multiplying the variable. But when you have something more like 4 theta to the 4th power, well, in that case, it's important to show the UDU setup, all right? And that's going to go from 0 to pi over 2. All right, so that reduces first of all to 9/4 theta minus 9/16 sine 4 theta from 0 to pi over 2. So f of upper limit and minus f of lower limit. That's basically the fundamental theorem of calculus. So 9/4 pi over 2 minus 9/16 sine of 4 times pi over 2 minus, okay, do we agree that if we substitute the lower limit of 0 to both terms right here, that's going to get a big 0? Well, number one, 0 times 9/4 is 0, and sine of any multiple of 0, isn't it 0? So big 0. Right, just to denote that we are skipping these calculations. It's fine if you do that on the final exam, right? And well, that's 9 pi over 8, and this will be reduced to say sine of 4 pi over 2. That's sine of 2 pi, which happens to be what value? 0. 9 pi over 8 minus 0 is 9 pi over 8. All right? And just as a quick note, this is a final exam question, okay? That's a final exam question. That's one of those that I'm going to give away, like, hey, expect to see something like this. All right? Let's see.